Hey everyone, my name is Vinelin, and in this video we're going to have a look at how you can fine-tune a Tiny LLM on your own dataset. We're going to start with preparing the dataset for training, then we're going to have a look at what parameters you need to set in order to get your tokenizer and model prepared for training along with LoRA setup. Then we're going to train the model within a Google Cloud Notebook free tier. Finally, we're going to load the trained model and do evaluation on a test set to see whether or not the fine-tuned model is doing a good job. Let's get started. If you want to follow along, there will be a complete text tutorial along with the link to a Google Cloud Notebook for this video, and this will be available within the bootcamp section of MLExpert.io, and then fine-tuning Tiny LLM on custom dataset. This is available for MLExpert Pro subscribers, so if you want to support my work and get access to this, please go and subscribe to MLExpert Pro. Thanks. So what do you need in order to fine-tune a Tiny LLM? First, we're going to go through why you might want to choose a Tiny LLM over something like Llama 7 billion parameter models. Then we're going to have a look at why you would need to do some fine-tuning. Then we're going to have a look at some of the checkpoints that you need to cover in order to choose and prepare your dataset. And finally, I'm going to give you some tips in order to fine-tune a Tiny LLM using LoRA. So why Tiny LLMs? First and most importantly, those types of models are relatively small or smaller compared to regular large language models, such as 7 billion parameters models such as Mistral or Llama 2. And Tiny LLMs are usually something like TinyLlama, the one that we're going to use in this video, and other like Phi and Phi 2, which is on the, let's say, limits of what I would call a Tiny LLM. Another important thing for Tiny LLMs is that you can do much faster inference with those, and the training itself can be a lot faster compared to what you might get with a relatively larger LLM. And you can even use like older GPUs in order to train those types of models. And finally, even though those models are tiny, some of those are still trained with very high quality data, such as Phi and Phi 2, and trained on a lot of tokens in the dataset, such as TinyLlama, which has more than 3 trillion tokens in the training dataset. Why would you want to do some fine-tuning? Well, first, you can try to start with some prompt engineering, and if that works for you, and the benchmark or the performance of your model is relatively good, then try to stick with just prompt engineering. But if you want to increase the performance of your model, and if you have enough data in order to do that, fine-tuning is a very good approach in order to get much better performance of your Tiny LLM. And in the general case, Tiny LLMs are not as powerful at 70 billion parameter model plus, like for example, Llama 2 or Mistral or other models, and not even close to ChatGPT and GPT-4 and GPT-4 Turbo. So in that case, if you want to have some much smaller model that is performing relatively well on your benchmark, on your tasks, you would likely need to do some fine-tuning in order to provide much better performance for your Tiny LLM. Another good thing about fine-tuning is that you are going to reduce essentially the number of tokens that you need in order to pass into the input with the prompt. So you might just pass in your data, and you might just want to think of a much smaller template that will be good for your prompts, and you can essentially just use that instead of some larger prompts, and this will make your inference time even faster. Of course, you might want to have a data, or might have data that is private to you or your company. So when you're fine-tuning your own models, essentially you don't have to expose the data to the outside world. So this is another, let's say, positive of the fine-tuning approach. And how would you prepare your data? As a general rule of thumb, I would suggest more than 1,000 examples that are of high quality. So preferably you might want to have humans that were looking through the data, and they would essentially get a feel of where the data quality is, And when you get a good quality data, your fine-tuning LLMs are going to be much, much better compared to if you have some, let's say, shady data points. And you would have to think about what type of tasks you're solving. In this video, I'm going to show you that we are going to use the LLM for 2 different tasks, which is very good. In the past, if you had to solve for multiple tasks, essentially you had to train multiple models or have a single model that have multiple heads for each prediction. In the era of the LLMs, we are going to just say that we want 2 outputs. One will be the sentiment of news, and then is going to be the subject of the news or cryptocurrency news. This is the dataset that we're going to use. And you would have to have a look at how much tokens do you need in the input and the output, and have a look at your model maximum context width and choose whether or not you're going to be able to fit the inputs and the outputs within the context window. And then you would have to think of a template that is going to be essentially good in order to prepare your own data. The dataset that we're going to use is these Crypto News Plus that are available on Kaggle. And it says that those are crypto news articles containing title, text, and sentiment analysis. Of course, the sentiment analysis is going to be essentially probably predicted from some models, so the labels might not be perfect, but still this is a real world example of what you might have. And here is the crypto news data for over a year, 21 to 23. Structured format including title, text, source, subject, and sentiment analysis. And this is the example of data that you get. You have quas for the sentiment, polarity, and subjectivity. And of course, you have this subject, and all of those are going to be accompanied with the text and a title from the news. This is just the first paragraph of the article, and this is the title of the article. I have a Google Colab notebook that I've loaded the crypto news data, and I essentially took the CSV or the original CSV file and created this stratified split between train, validation, and test sets. And here is the data frame for the training head, training data frame, and you see the split between the training, the validation, and tests examples. We still have a lot of data, and you see that I've got the subject here, and I essentially split the sentiment within a couple of columns, so this will be a bit easier to work with compared to what we had into the original data set. Other than that, I'm going to show you the splits between the train, test, and validations. So you can see that the stratified sampling has worked wonders for us. You see that the train, the validation, and the test set for each subject, which is Bitcoin, altcoin, blockchain, Ethereum, NFT, and DeFi. All of those are split pretty much as the way that the training set has the frequency for those. And you see that essentially we have a very large bias towards Bitcoin, altcoin, and blockchain examples, which is again something that you might not want in your dataset, but this is the real world in here. You can of course use some techniques such as oversampling, undersampling, etc. in order to fight this, but just for this fine-tuning example, I'm going to stick with the original distributions. This is the subject that we're going to try to predict, and then we have the sentiment. Again, the distribution is essentially kept as in the way that the training set has this. So again, with the stratified sampling, and you see that we have the positive, neutral, and negative sentiments. And you might see again that we have somewhat of a skew data towards neutral and positive news, while the negative news are much less compared to the neutral and positive. So keep that in mind as well. And this is the subjectivity score, something that we are not going to predict, but I've shown this in order to get a feel of this category distribution. So the first thing that I'm doing here with the dataset in order to pre-process it is to essentially get the dataset from pandas, and I'm going to use the Hugging Face datasets library. I'm going to just create this dictionary with the train, validation, and test subsets. And then I'm going to essentially load the tokenizer for the model that we're going to use. In our case, this is going to be the TinyLlama model. and I'm going to get the latest model that is not a chat model. And this was trained on 3 trillion parameter tokens. And I'm going to set a padding token or pad token for the tokenizer. And here you see that I'm getting the tokenizer for the model. Then I'm adding this special token for the pad token. And then I'm setting a padding side to right. And after loading the model itself, I'm going to resize the token embeddings in order to get the new token embeddings count, since I'm loading or adding this tokenizer, and I'm expanding this to a pad of multiple of 8. And you see that we've added this token, the padding token that is, and you see that now the tokenizer has all of the available tokens, and this is the new token that we've added to the tokenizer. So this is very important, because if you don't have some padding or correct padding within the training sets, your model is tending to essentially repeat the last couple of words or tokens that is going to generate. So this really helps with the repetition of the models. And then another thing right here is that if you're using a GPU that is capable of using flash attention 2, I would strongly suggest you that you turn on this one. But since I'm using the T4 GPU, which is available on the free tier of Google Cloud, I'm essentially commenting out this one. So essentially this is how you're going to load the model and the tokenizer itself. Next, we are going to make sure that the number of tokens are going to be fitted right within the context window of our TinyLlama model, which has 2048 tokens of context width. And in our example, I'm going to create this format or template, which is something that I've chosen to use. This is not something standard. So I chose to set the title, the text, and then the prediction in this format for the article or the news article. And then you see that within the prediction, I have this subject and then sentiment. And in order to have a look at how many tokens we are going to need, I'm essentially counting the number of tokens in each example after formatting it into using this template. And you see that the number of tokens is much more lower compared to the maximum limit of 2048. So we are going to essentially need at most 200 tokens for the input. So the problem with the context window should not be anything at all. Our examples are very tiny compared to what the TinyLlama model can handle. While you can fine-tune a Tiny LLM in its fullest, still 1.1 billion parameter models are not small by any means, even though the name is TinyLlama. So if you have a single GPU, for example, a T4 that we're going to use within the Google Cloud notebook, you might have a hard time fitting this model into the GPU and fine-tuning it on its own. So in our case, I'm going to have a look at how you can use LoRA in order to fine-tune the Tiny LLM. And this will allow us to even increase the batch size that we are going to use in order to train this model. So one important thing to note is that LoRA, or with LoRA, when you're training such models, you are going to essentially train just a small model called adapter on top of the original model. So you have to essentially load the original model within the memory and then create a smaller model or a set of or a matrix of parameters in order to fine-tune just those. And even though when you're training models such as Llama 7B, you might just train roughly or even lower than 1% of the parameters. If you do that with Tiny LLMs, you're going to get like something like maybe 1 or 10 million parameters in order to train your model. So in the general case, this wouldn't be enough. Of course, this depends on the task at hand. So as a general start, I would recommend something like 100 million parameters, which is a great start, and you can tweak that. In order to get something like this for the TinyLlama, we're going to increase the rank of the Llama, or the LoRA config to about 128. So this will give us roughly 8.5% of the parameters for training of the original model. And then I'm going to increase also the LoRA alpha in order to scale the learning rate and not change its value. And again, I'm going to set this number to 128. To start with the training, I'm going to set the pad token ID on the model, and then on the model config path token ID to the tokenizer token IDs. Then I'm going to have a look at model config in order to double check that the pathing token or path token ID has been properly set, which is. And then we are going to have a look at the model architecture, which is going to tell us where do we need to apply the LoRA scaling or the LoRA target modules. So in this case, you're going to see within my config right here that I'm targeting the self-attention one and then the MLP ones. So these are the linear layers and these are the self-attention layers, as you can see right here. And I'm essentially targeting all of those. And for the rank of the matrix, and shout out to Trellis Research's YouTube channel, from which I've seen that he's actually targeting tiny LLMs with much higher number of parameters. So thanks to you. I've seen that you need to actually increase the number of parameters or the ranking of the LoRA matrix in order to fine tune much better with tiny LLMs. And here I'm going to set the rank of the matrix and the LoRA alpha in order to scale the learning rate within 128 both, and I'm going to apply a small dropout to the LoRA. So this is the new adapter model. And then I'm going to set that this is a causal language modeling task from the task type right here. And then I'm going to get the path model on top of the original TinyLlama model with the LoRA config application right here. And you see that we are actually targeting roughly 100 million or 101 million parameters for training, 8.4% on the training front with the LoRA. So next I'm going to show you how you can train just on the completions. And this is something that my colleague called Wucho have shown me. Thank you, Wucho, for that. So instead of training the whole text or using the whole text for the training, you essentially what you want to get is to use, for example, from this example, you want to calculate the loss only on these. So essentially I'm going to ignore this, which is the changing part within the dataset. And to calculate the loss, I'm going to essentially take only those tokens in order to have a look at how well the model is performing. And this will drastically reduce the loss that you have. But keep that in mind that if you're training for a task such as our own right here for some completion, just for some completions, then this type of collator is doing a great job. But if you're training for something like assistant and chats, etc., this might not be a good use case of the data collator. So keep that in mind. And in our case, I'm going to use the prediction as a template. I'm going to encode this, and then I'm going to pass in the template IDs or the response template IDs to the collator, and then I'm going to pass in a tokenizer to that. So essentially what we are going to do here is to tokenize the template, since without that this collator appears to be failing, at least for me. And I'm going to essentially get a single example and tokenize it in order to show you what the labels this collator is going to add. So you see here that when I create this data loader and I get the next batch from it, you see that now we have input IDs, attention mask, and then a new field called labels. If you look through the batch labels, you see that everything before the template essentially has been given an ID of -100. So this is essentially ignore these tokens. And for the loss itself, only these tokens are going to be used for the calculation of the loss. Since we get a bit of repetition with the subject and sentiment, you can essentially prove this to be either better. So essentially what you might want to get is to get rid of this and get rid of this and just print those two lines. This would probably be much better compared to what we have right now. And your loss is going to be performing even better. But yeah, this is an exercise that if you want to do this. And then for the training arguments, I am going to essentially use a batch size of 4, but I'm going to multiply that by 4 in order to get an effective batch size of 16 using gradient accumulation. So what this will do is going to be passing only 4 examples through the GPU, but then the results are going to be accumulated within 4 iterations of those 4 batches, and then the accumulation or the gradient is going to be calculated on top of that. This appears to be helping with the training, and I've seen that during the training on this single GPU, this gave me a much lower much lower losses, so it appears to be helping. Then I'm going to be using a regular Adam with weight decay fix from Torch Optimizer. We're not using any quantized optimizers, since we are going to be using FP16 or floating point 16 training for this one. We don't need LoRA for those tiny language models. This appears to be training very fast, and it appears to be very stable with very good results. So no quantization on this part right here. And I'm going to essentially use a constant scheduler type. This is a bit redundant, since we're not going to be using any warm-up right here. And then another important thing is that I'm going to train just for one epoch. Of course, you might want to train for multiple epochs. That depends on the dataset size that you have. I've trained this for roughly 40 minutes, I believe. And if you train for longer, you might actually get better results with those tiny LLMs. So it might be worth to experiment with that. And those are essentially the training arguments that we have. And then I'm going to get this format prompts, which is going to be passing essentially example. And within this example, I'm going to, or examples, and within that, I'm going to essentially use the format of the template that we've seen thus far. And this is going to essentially create our batch for us. So this is the trainer that I'm going to use. I'm going to pass in the model, the training arguments, and then the training and the validation sets, a tokenizer, max sequence length, which can be increased, but in our case, that's not needed. Then the formatting function, which is this one, and then the data collator, which is going to be training only on the completions. So this is essentially the output of the training, and you see that the model is actually performing very well. This is the evaluation was from the TensorBoard training. You see right here that we start with a relatively high value of 0.15. Then after 600 steps, this is 0.11, below 0.10. And yeah, you can see that in a relatively, let's see that again, in about 26 minutes of training, we get this far below. So this is really good. And you can check the tutorial for the full outline of this, but this is my training was without any smoothing. And you see that this is again generally decreasing. You might argue that we are going to hit a plateau right here, but I would say that the training went really well. And these are again the results from this one. You see here in this table that we have the training was and the validation was, and you can see that they're fairly similar. And the validation was is actually a bit better in the later iterations, which is surprising, but it is within the realm of what you might get, since the training set is much larger compared to validation set. So it might be just randomness right here. And then in order to get this model to be saved, I'm going to use the trainer model save pre-trained. And within the same folder, I'm going to essentially get the tokenizer to save itself as well with the proper configuration. So in order to try out our model, I'm going to essentially, at this point, I've restarted the Google Lab notebook. And what I did here was to get the base model, load it into float 16, and then apply the PEF model on top of that. This is again the same folder and trained folder. And then I'm going to essentially merge the PEF model on top of the original model. And this is going to get again the tokenizer, which was correctly formatted. You can see right here that we have a padding token, and we have a correct padding site and a correct pad token ID. And after that, I'm just again setting the pad token ID and config pad token ID just in case. And now we can use our fine-tuned model as a regular Hugging Face Transformers model. I'm going to create a pipeline out of it for text generation. I'm going to pass in the model, the tokenizer, the maximum number of new tokens. This is going to be only 16 since we already know that our model is going to be producing a very small number of tokens for the completion. And I'm going to essentially format the example for completion or for prediction. I'm going to just take from the example the title, the text, and then I'm going to pass in the prediction without the prediction itself. I'm going to reduce the verbosity of the logging, and then I'm going to have a look at 10 examples. Note here that this is the text, so this is the complete text from the example, and then I'm calling format for prediction right here with the example itself, and I'm going to essentially output the prediction. So the original subject or sentiment is not passed into the model. So this is the first example, Binance Research report reviews, etc. And the subject here is from the original data point is NFT, the sentiment is positive, and this is now the prediction. You see that we have a duplicate of the sentiment wine by the model. This is relatively common, and we are going to address that in a bit. But the subject appears to be correct right here, and the sentiment appears to be positive as well. Let's look at the another one. Subject altcoin, sentiment positive, altcoin positive. Again, this is essentially what we have right here. It is correct. Then subject Ethereum, sentiment positive. Again, those appear to be exactly correct. Altcoin positive, but the prediction was negative. Let's have a look at the title. Coinbase CEO calls for regulation of centralized crypto entities. The demise of FTX has set back crypto by years, and this disaster is likely to steer regulators into action. So the sentiment is positive, but I wouldn't exactly agree with this label right here. You can decide on your own. And I think that our model is actually predicting a better sentiment than the one in the labels. Something that is very interesting. Let's have a look at another one. Altcoin positive, again, correct. Now, this subject here is altcoin, but the model is saying Bitcoin. Let's have a look at, and there are again positive sentiments for both. So Bitcoin's prediction as BTC breaks through, etc. Bitcoin, the world's largest currency, and the label is altcoin. Yeah, our model is performing very well indeed. So this looks to be the case that the labels are not exactly perfect, but our model seems to be doing a good job, even though the dataset is not of that high quality. And yeah, you can go through a lot of examples and see for yourself. So next, I'm going to do something a bit different. I'm going to extract the prediction for the complete test set. Again, this is a 1024 242 examples. This took about 10 minutes. And these are the predictions. The title, the text, true subject, true sentiment, predicted subject, predicted sentiment. This is essentially the data frame that we're going to get. And I'm going to essentially calculate a very rough accuracy for the subject, which is, according to this calculation, 78.6% accuracy. Of course, you might want to go through some examples and see for yourself if the model is actually better compared to the labels. This is essentially a heat map or a confusion matrix of different predictions for the subject and the real values. You can see that we have some overlap between blockchain and altcoin right here, but nothing really major. And again, for the true subject and the predicted subject, let's see. Let's get an example from right here. AI optimizing crypto exchange functions, artificial intelligence tools are providing. So the true subject is Bitcoin, but the predicted subject is blockchain. Yeah, at least from the first couple of words, it appears that, again, our model is performing better than the labels, but I might be wrong. I mean, go over the title and the text for some examples on your own. Next, for the sentiment, we have exactly the same calculation. And you see that this time we have just a tiny bit over 90% accuracy on the test set, which is really impressive with such a small data set. Again, this is the confusion matrix. Yeah. And again, we are going to have a look at some examples. Bad news is good news. Bitcoin plays with USD. Bitcoin reaches its highest target in nearly 7, etc. And here the sentiment is positive, while our prediction is neutral. I would agree that the labels here is better compared to what we have in the model itself. Brian Armstrong promised me 100 in Bitcoin. Is it possible that Coinbase CEO, etc. neutral? And our prediction is negative. I'm not sure. I have to see the title and the text for this one. But yeah, even if this is correct, 90% is very good for such a small training. So this is it for this video. You now know how to fine-tune a Tiny LLM on your own dataset, and you know how to set up correctly the LoRA configuration for that. And also you know how to save the model after training and then get the final model on top of the original model and do some inference with it. In the next video, I'm going to show you how you can use the adapted model and fuse it or merge it within the original model, push that to a Hugging Face hub repository, and then from there, we're going to deploy the model in production behind an API, and we're going to start to get some inference on top of a real-world example. Thanks for watching, guys. Please like, share, and subscribe. Also, join the Discord channel that I'm going to link down into the description below, and I'll see you in the next one. Bye.